Greetings. So, we begin this course on quantum mechanics. It is an introductory course, but the subject is vast. So, I like to call it as select topics in quantum theory, because the subject is vast and we can make an attempt to address only some of the aspects of this topic. So, the first lecture will be a discussion on why we need a new theory of mechanics. So, the earlier theory which physicists used is what we call as classical mechanics, and the reason it is called as classical mechanics is because what you understand by the term classical. So, you know what is classical literature, classical music, right? Classical music has withstood the test of time for hundreds of years. So, it has lived long. So, that is classical. Classical is something which has stood the test of time. So, the earlier theory which stood the test of time is what we refer to as classical mechanics. It is indicated on this slide by Newton's picture with the falling apple. Although the story of the falling apple is exaggerated, Newton perhaps did not discover or he did not formulate the laws of mechanics sitting under an apple tree, but it is a nice story anyway. And then this theory needs to be superseded by a new theory, because it meets some limitations, it does not work, and then it is replaced by quantum theory, and quantum theory leads to some very challenging questions. It requires you to deal with some ideas which are counterintuitive. Our intuition suggests that okay, this is what reality is, this is what the physical universe is about, and quantum theory makes you come to terms with a different view of reality altogether. So, it is almost sickening, because it involves many shocking new ideas. There are ideas about uncertainty. So, even as much as this course is an introductory course, I assume that you have some familiarity with quantum theory, you have come across these terms, you know, you have heard about the uncertainty principle, you have heard about the Schrodinger equation and so on. So, I will assume a little bit of familiarity with the subject, but then I will introduce all of these things from the very foundation. So, the uncertainty principle is a very challenging idea. Then it involves the principle of superposition, that a physical system can possibly be in a state of two superposed states, which we normally consider to be mutually exclusive. Means you know that a man is either dead or alive, and what is true for a man is also true for a cat, and it was the cat's state which Schrodinger talked about, and he came up with the idea of entanglement to explain this state of the cat, that it can be a superposition of state which involves the cat being alive and another being dead. So, so these are rather contradictory states, but then quantum theory requires you to consider superpositions of such states, and you have to come to terms with that. So, we will discuss this, and this is perhaps the essence of quantum mechanics, the entanglement, the superposition principle, and is an extremely, it is an important cornerstone in quantum theory. So, quantum theory was developed by several people in the last century, and Planck made an important contribution to it. Planck's work was subsequently developed by Einstein, then Heisenberg, Born, Jordan. They wrote a paper which is famously known as the three-man paper. This was a very important paper which contributed to the development of quantum theory. And then of course, there were the postulates of Louis de Broglie about the wave particle dualism, and then the Schrodinger equation which described the wave function which was proposed by de Broglie. The Planck hypothesis which Einstein developed was subsequently consolidated in the statistical interpretation of the electromagnetic field in the works of Satyendranath Bose, and these are some of the main contributions to quantum theory. So, you normally talk about two alternative approaches to quantum mechanics. One is what you call as wave mechanics, okay, and this is the approach which was developed in the language of de Broglie and Schrodinger, and the other is matrix mechanics which was developed in the language of Heisenberg, Born, Jordan and so on. And subsequently von Neumann and Dirac, they interpreted this. In fact, Schrodinger himself had established that the wave mechanics and matrix mechanics are completely equivalent. But then Schrodinger and Heisenberg continued to criticize each other's approach, saying that the other one sort of stinks. But the equivalence of the two approaches was established by Schrodinger himself, and in the language of von Neumann and Dirac, it was very firmly interpreted that these two are representations of the quantum theory. So one can say that there are these two different developments, two approaches to quantum theory. So at the foundation you have got the quantum theory, and then wave mechanics is one representation, matrix mechanics is another representation, and another development of quantum theory is in terms of Feynman's path integrals, which perhaps people do not so much talk about, but I think in this course I will include a discussion on this topic as well. So these are the three approaches to quantum theory: wave mechanics, matrix mechanics, and the path integrals of Richard Feynman. So here is a figure, and this figure has been made courtesy to Uday, who has done a simulation of the Young's double slit experiment, and of course there is something further that he has done on this, but I am happy to use this figure. This experiment is the Young's double slit experiment, and it really contains the heart of quantum theory in many ways. This is an illustrative experiment. It stands for what quantum mechanics is about. In fact, Feynman has got a very famous lecture in which he says that, okay, this has got everything about quantum mechanics, and there is nothing in quantum mechanics which is outside this. So this is really an important experiment to consider. So you have a source of light, and the light waves or light particles, however you want to interpret them, would go from slit 1 or slit 2, and if you think of this as a wave front, then the division of wave front will allow part of the amplitude to get out of the slit 1 and part of the amplitude to get out of slit 2, and then when it reaches any point on the screen over here, you will have an addition of amplitudes of the waves which are arriving there from different virtual source points. Okay, so S1 and S2 become the source points, and waves arrive at a screen from different source points, and what happens is that the amplitudes of the waves, they add up, and the intensity is given by the square of the sum of the amplitudes. Intensity is not given by taking the amplitude square of each component and then adding up all of those intensities. Now that is the reason you get interference. Okay? So you get dark and bright fringes, and this is a very stunning experiment, because if you close one slit, okay, you get a distribution which you expect. If you open that slit and close the other one, again you get an intensity distribution which you would expect. Okay? And now go back to this consideration that you have got only one slit open and you have got an intensity distribution, and now you open another slit, and where you had an intensity distribution, suddenly you find that there is darkness. So, by having an additional source, by opening another window through which you are admitting light, our intuitive thought would be that the intensity over there would increase. It does not happen. On the contrary, the intensity gets distributed or redistributed, and then at some place you have intense bright fringes, and at some places you have dark fringes. So, this is a very weird kind of phenomenon, and then you obviously want to ask, where did the light pass from? Did it pass from slit 1, did it pass from slit 2, and so on. And if you make an attempt to find what is the path which the light has taken, then the interference is destroyed. As long as you do not make an attempt to find that path, then you find that if both the sources, both the slits are open, you get an interference pattern. So, this is a very counterintuitive idea which you cannot explain in terms of classical mechanics. Okay? What is even more alarming is that you can have all kinds of paths. For example, you can do this experiment not just by light, but you can do it also with particles. And Feynman talks about this, which is the experiment with bullets. And the experiment with bullets, you can actually do this experiment. I think when Feynman discussed this, this was in the early days of 1960s, 61, 62 or something, it's long back in the lectures he gave. At that time, this experiment was not done. It was only a thought experiment in Feynman's mind, but he used it to illustrate it. Subsequently, this experiment has been done, and I think it was first done in Japan and then subsequently at a few other places also. But then you actually find that this experiment, if you carry out this experiment carefully, you do find the predictions which you find in Feynman lectures. So, what happens is that if you carry out this experiment with electrons and you have a certain idea of an electron, you have got a certain idea of a bullet, you think of it being something like a tennis ball or a cricket ball, but a very tiny one, an extremely tiny one. So, that is your idea of a particle. You think of the particles of sand which you have seen at the beach, right? And whenever you talk about particles, the picture that comes to your mind is that of cricket balls, tennis ball, sand particles, dust particles. Okay? So, you have got a very clear image of what a corpuscle, what a particle is. Now, if you have a particle, it would go through either slit 1 or slit 2, and it is hard to imagine based on our experience that it would possibly go through both. It would go through either slit 1 or through slit 2. Like this room has got 2 doors, and you walk in and walk out through one of them, and you are not going to do it through both. So, it is exactly the same kind of challenge that you have to face when you are dealing with this Young's double slit experiment with electrons. So, you think of a particle and it can take all kinds of paths. So, you have got a path which originates at the source, it can come through this, it can get scattered, okay? And it can get scattered, and if it hits some other obstacle, it can get scattered again. Now, till it gets scattered by this obstacle, it would continue to go straight. That is pretty much like the classical trajectory. Okay? But then if it meets an obstacle, so in between the interactions, in between the collisions, the path would be a straight line. But then if it gets scattered, and now you have got a screen over here, and I have shown this path to go through this screen. Now, what the heck is happening over here? Yes, it can, and this is the tunneling that you are confronted with in quantum mechanics. Okay? So, we will deal with these ideas as we go along. It can get scattered again and then go through here, and then eventually if it reaches a certain point, okay, then once again you have to find what kind of a pattern you will get if you measure the counts of particles which arrive at a particular point on the screen as a function of distance from the center. So, O is the center of the screen, and a distance along the screen away from O will be a measure of where the particle arrives, okay, and the number of particles arriving over there will not be uniform if both the slits are open. What you will get once again are dark and bright fringes. Now, this argument works if the scattering takes place anywhere means anywhere in the universe, and in fact Feynman talks about it being scattered from the Andromeda galaxy. Okay? So, the paths can go all over the universe, and all of these paths can be taken into account. Many of these paths end up cancelling each other. That is a matter of detail which we will talk about when we discuss Feynman's approach. But essentially what is happening over here, that the manner in which probability adds up in classical mechanics is different from how it adds up in quantum theory. Now, strictly speaking, this statement should be made in a somewhat different way, because particles are not going to follow one set of rules if you want to use classical mechanics and if you want to use quantum mechanics. Okay? Particles will follow the laws of nature. Okay? Your interpretation of that is going to be different in classical mechanics and quantum mechanics. Okay? So, the particles will only follow the laws of nature, and the laws of nature are essentially quantum. Okay? So, we will introduce ourselves to this, and what is central to this, as you recognize from our discussion, is how the probability adds up. Now, we are familiar with probability even in classical mechanics. Okay? It was responsible for the Mahabharata war, right? Because when you throw dice, there is a certain probability with which the dice will fall one way or another, and there is nothing new about it. I mean, you can toss a coin and you can get either a head or a tail. These were different kinds of dice 5,000 years ago. I don't know what Shakuni used, but sure enough, the game of probability was known. Okay? Now, probability and statistics, the way it enters quantum mechanics, is again very different from how it enters classical mechanics. Okay? In classical mechanics, it enters because there are a number of different possibilities which are accessible to the state, and then based on the information which is available to you at that particular time, instant of time, it would be hard to predict how the coin will land. So, if I take a coin and toss it, okay, it will be difficult for you to call heads or tail. But if I give you all the forces acting on the coin, I tell you where the torque is applied, okay, I tell you what is the resistance it is meeting in the air, okay, and you have got a supercomputer on which you can carry out all of these calculations in details, and you know the height to which it goes, you will be able to predict exactly how it is landing. So, there is no intrinsic lack of ability to predict. The lack of ability comes from the fact that there are many variables which you have not defined. So, there are these hidden variables which you have not really spelled out, and that leads to a certain statistical uncertain behavior. In quantum mechanics, it is intrinsic to nature. It is not because you have missed out on some information. So, statistics enters quantum mechanics in a very different way. It is intrinsic to the laws of nature. You cannot hope that okay, if I put in some additional information I will get certainty rather than the Heisenberg uncertainty. It is only because there is some missing information. And all of these questions were very important, and Einstein himself did not believe that probability was intrinsic to the laws of nature. So, this is famously Einstein is quoted over here that God does not play dice, and Niels Bohr argued this. So, these are very famous debates in 1927 between Einstein and Bohr, and on many occasions Einstein came up with thought experiments to prove that this statistical nature of quantum theory could not be correct, and Bohr ended up showing a fallacy in Einstein's argument. So, he would say that it is not your business to tell God what to do. Okay. So, the Solway Conference is a very famous landmark, is a very important landmark in the development of quantum mechanics in 1927. So, Einstein's viewpoint was this, that the question is about what is reality, okay? And Einstein's interpretation of reality was that it is a condition which a physical system would have, so that it would be possible for that physical property to have a certain value with or without a measurement. Now, the premise of the uncertainty principle is that position and momentum are not simultaneously accurately knowable, okay? And the argument that goes with it is that if you make a measurement of position, you lose information about the momentum and vice versa. So, Einstein's position was that okay, I do not make a measurement, okay. You are arguing that I am losing information about the canonically conjugate variable because I made a measurement. I will not make a measurement, I will sit quietly, but I maintain that the object does have a well defined position and a well defined momentum. I am losing that information only because I am making a measurement. So, if I do not make a measurement, it is not that it does not have that value, it has that value, okay? And I am not able to get it because the measurement is disturbing it, and then I have to find out some other way of getting those values without carrying out a measurement, but that is the reality, okay? So, this is something which Einstein dramatized this by asking, is the moon there if nobody is looking at it, okay? So, certainly you believe that the moon is there, it's all right, and it is there even during the day when you do not see it, and it is there on the Amavasya as well, right. But we certainly believe it, but this is the classical idea, okay. And Einstein's conclusion was that the description of reality given by the wave function in quantum mechanics is not complete, because it deprives you from getting accurate simultaneous information about canonically conjugate variables. Okay, so, this was Einstein's position, and this was the big debate between Albert Einstein and Niels Bohr, which Bohr always won hands down. In fact, once to prove Einstein wrong, he ended up using the theory of relativity and proved that Einstein's argument had a fallacy because Einstein had missed out. So, great minds, okay, and these are some of the most exciting controversies, most exciting debates between Bohr and Einstein. So, entanglement is intrinsic to quantum mechanics according to Bohr, whereas Einstein maintained that yes, there are consequences of entanglement, but it is because some information is missing, and if you can put that information into the system, then you will recover causality. That was Einstein's hope. So, this was a big debate between Einstein and Bohr. And subsequently, there is a very famous paper by Einstein, Podolsky and Rosen, in which they challenged the statistical idea. This is called as the EPR paradox, the Einstein-Podolsky-Rosen paradox, and in which they challenged the statistical nature of quantum mechanics. And subsequently, John Bell, he came up with this work in 1964, in which he developed a formalism in which you can mathematically test if the probabilities that you get out of the kind of argument which Einstein had advanced and the kind of probabilities you get from quantum mechanics. So, can the gap be filled by adding the information which Einstein said was missing, and then you can come up with some sort of inequality. So, we will also discuss this at a later point in the course. So this is just to give you an indication of what are the challenges that quantum theory went through before it came to be accepted, and now all of us use it routinely as if it is correct, even if we do not believe in it. So, these are some important elements in the quantum theory. You have got the superposition principle, which is intrinsic to quantum mechanics. Entanglement is intrinsic to quantum mechanics. Okay. Einstein challenged it, Bohr defended it. Okay. And then a system, however, when you carry out a measurement of the system, you end up finding that it is in one of what is called as an eigenstate. Okay. So, the system collapses in what is called as an eigenstate. Eigenstate is its own state, and this is something which I will explain by using by referring to the Stern-Gerlach experiment, which was one of the first experiments in which this idea came out very neatly. So, this was an experiment which was carried out in 1922, and what this experiment involves is that you send silver atoms from an oven through a magnetic field, and what you expect from the silver atom, that okay, silver has got how many 47 protons and 47 electrons. So, in the outer shell there is a single electron, which is the 5s1, and if you assume, and you have to assume because you do not have the theoretical framework to come to this conclusion, that the electron has got an intrinsic angular momentum and an associated magnetic moment, and this comes from what we call as the electron spin. Now, electron spin, the word spin is classical. It makes you think about the earth rotating about its axis. The electron spin is not that. You are using that word, but with a new meaning, and the new meaning is something that we will discuss only when we analyze this in terms of the relativistic quantum equation, which is the Dirac equation rather than the Schrodinger equation. Okay. So, tentatively I will anticipate the result and acknowledge that the electron has got intrinsic angular momentum and a corresponding magnetic moment, and this magnetic moment it will make its path go two ways, whereas if you do not think of this intrinsic angular momentum, you will have a classical result. Okay. So, this is the experiment which was done in 1982, and the spin has the electron spin being a fermion, it is a half integer spin. In fact, if it is half h cross in units of the Planck's constant by 2 pi, and this is something which we today discuss in terms of what we call as Pauli matrices and so on. I will come to that a little later, There is an exclusion principle which Pauli had advanced in 1925, but the spin itself was not known at that time. It was not known that there is an intrinsic angular momentum. It was not known that it has an associated magnetic moment associated with an intrinsic angular momentum. There was an exclusion principle, and the exclusion principle was necessitated by the fact that when you look at the periodic table, and the chemical properties of atoms were known, and there are chemists over here. So, you know that the periodic table had to be explained, the Mendeleev and so on. And what you use is the Aufbau principle, okay, to start filling in the number of electrons. And to go from one row to the next, you need to close one all the possibilities for one principal quantum number, and once you exhaust that, you go to the next row. Okay. So, to do this filling, what Pauli recognized was that in addition to the 3 quantum numbers which were understood at the time, the n, l and m, you needed a 4th quantum number which could have 2 values. You can call those 2 values as north and south, or 0 and 1, or a donkey and a horse, whatever. Okay, it does not matter, because it was not known that this was angular momentum with a particular value in units of h cross. So, the Pauli's exclusion principle was that no 2 electrons in an atom can have the same set of 4 quantum numbers, but the 4th quantum number was not thought to be the spin quantum number as we know it now. And this is an idea which was developed a little later, around the same time, but a little later, when it was proposed by Uhlenbeck and Gaudsmit, when they were carrying out some experiments in the laboratory of Paschen, and they found that to account for that experiment, they had to postulate an additional angular momentum, which they called as the spin. And these are the pictures which come to your mind when you think about angular momentum. You think about an orbital angular momentum in terms of the Kepler model, and the spin angular momentum in terms of a spinning top or the earth going around the axis. Now, both of these models are wrong, and this is one of my favorite slides in which I alert my students that if you use these models, 3 ghosts will come after you. One is Pauli, the other is Dirac, and the third is me. Okay? So, these models are not to be used. These are classical models. Both the angular momentum and the spin have no quantum analogues. These are essentially quantum properties, and we will have to learn by learning quantum mechanics what the angular momentum is, and what is the orbital angular momentum, and what is the spin angular momentum. So, these models are not to be used unless you are happy with the 3 ghosts. Okay. So, the idea of electron spin was introduced by Uhlenbeck and Gaudsmit, and Uhlenbeck himself called it as abracadabra. This is the famous keyword which magicians use. They want, when they want to get a rabbit out of a handkerchief, they just play with the handkerchief and they say abracadabra, and then nicely the rabbit comes out. So, Uhlenbeck said that okay, it worked. All right, but it worked like magic, not because anybody understood what it was. The understanding came a little later. In 1927, Pauli introduced the 2x2 matrices, and the real understanding of electron spin comes only when you look at the Dirac equation, the relativistic quantum equation in 1928. Okay, and then of course, Pauli himself proved the spin statistics theorem of quantum field theory. So, Pauli made huge contributions to the understanding of electron spin. So, we all think of it in terms of spin itself, spin in terms of Pauli's contributions, but initially Pauli did not have this idea that has now been established. So, we go back to this experiment. So, you have got shaped magnet over here, and then you have got this oven. You fire silver atoms, they go through this, and then they go to a detector. This figure is straight out of Sakurai's book, Modern Quantum Mechanics, and you can look up the details in Sakurai's book. Okay. And if you do this experiment, then you have got the electrons going out of this, and you would expect a distribution which is centered if your expectation is completely based on classical mechanics. Now, what is observed is that you get this one. There are two. Now, this itself is a quantum effect, because spin is an essentially quantum property, and not only a quantum property, it is a relativistic quantum property. It needs both relativity and quantum theory. Okay. So, now let us do this experiment, the Stern-Gulrach experiment, and these figures are straight out of Sakurai's book. So, you have got the oven and silver atoms come out of it. You have a silver Stern-Gulrach experiment which has got a magnetic field along the z axis, and you get two components, one along what you call as z plus, and the other component that you will call as z minus. And you can block this and send this through another Stern-Gulrach experiment. Okay. And now again you will have the same kind of magnetic field, and what you find in the result on the right is the z plus component. So, it is the z plus component which came out of the first Stern-Gulrach apparatus, and from the second the same comes out, and the minus component was blocked over here, and it is missing over here as well, as you would expect. So, this is fine. Okay. Now, you can have another 10 or 20 or any number of Stern-Gulrach apparatus, and every time you make a measurement, you will find that only the plus z component gets through. So, this is something that is narrated by saying that what a measurement does is that the system collapses into one of the eigenstates. Okay? And if you perform the measurement again, and that is what the second magnet is doing, that is what the third magnet will do, that is what the 10th magnet will do. So, if you keep repeating these measurements, the system which has collapsed into an eigenstate will remain in that eigenstate, and you can measure it any number of times and you will recover the same result. Okay. Now, what you can do is do this experiment in a slightly different way, and notice that in the previous experiment I had the magnetic field along the z axis here and also along the z axis here, but in the second experiment I first send it through a magnet whose magnetic field is about the z axis, but the second Stern-Gerlach experiment is done with an apparatus which is rotated through 90 degrees. So, this magnetic field is about along the x axis. Now, what have you done? You have blocked the z minus component, it is only the z plus component which goes, but then what goes in is in a state of superposition with respect to the x axis, and therefore, the x minus and x plus both components come out. Okay. That also seems to be all right, not so bad. Okay. But now, see what happens. Now, you have a third magnet. Okay. You have the first one which is along the z axis, the second along the x axis. In the first one you have blocked the z minus, okay. In the second you block the x minus and you have only the x plus going, but the z minus was already blocked over here. So, it did not even enter this apparatus. It did not even enter this apparatus, but it comes out of this. Now, what the hell is going on? Okay. And I wish I knew how to do this when as a child my parents were stopping me from having too many chocolates, and my dad would remove a set of chocolates and my mom would remove another part of the remaining things, and then I wish I could discover what my dad had already removed. So, this doesn't happen, right? Do you see how shocking it is? And this is quantum mechanics. This is quantum mechanics. And this is not just quantum mechanics, this is nature. Nature behaves according to these laws. What quantum mechanics does is to give you a correct interpretation of these laws. It formulates the laws of nature in a correct manner. Okay? So, this is what nature is about. So, it is not correct to say that quantum mechanics gives you a result which is different from that which classical mechanics does. It is more appropriate to say that quantum mechanics gives you the correct description of nature and classical mechanics does not. Because classical mechanics does not give you a viable understanding of the laws of nature. It fails. Okay? It has to be superseded, and that is what this first lecture is about, which is to give you a rationale excuse me, for which demands replacing an older theory by a newer theory. So, entanglement is intrinsic to quantum mechanics, and this word was introduced by Schrödinger himself. And now that you know that quantum mechanics is really shocking, you will derive some satisfaction from the fact that you are not the only one to be shocked. Bohr said that if quantum mechanics has not profoundly shocked you, then you haven't understood it. Okay? Let me alert you that if it does shock you, there is no guarantee that you have understood it. Okay, so be careful about it. All right? And in fact, Feynman goes on to say that I can safely say that nobody understands quantum mechanics, and that is a comforting line to read. Okay? But then it works, and it works because it is developed in terms of some very rigorous laws. It is a mathematical model which mimics nature, and the model works. It has been tested time and again, and there is not a single experiment done anywhere in the world for more than 100 years which is inconsistent with this model. Not a single experiment. Okay? So, it's something. So, what we are going to do is we may continue to be challenged by the concepts in quantum mechanics. We may continue to be shocked by how it describes nature in a counterintuitive manner, but if we understand the model, then we can use it to understand the laws of nature and perhaps even predict certain properties of nature. So, that is what learning of quantum mechanics is about, at least at an introductory level. So, the beginnings of course go back to this black body radiation, about which you might have studied in your high school and undergraduate college, and Planck proposed at a meeting that if energy in the black body radiation is interpreted in terms of bundles of energy, h times the frequency, then he could explain the spectrum, because otherwise all the other attempts to explain the spectrum met some sort of catastrophe, which made it impossible to interpret the black body radiation spectrum. So, Planck sort of proposed the quantum of light, but then look at what he admits later. He said that okay, it was purely a formal assumption and I did not give it much thought. Okay? He went on to describe it as an act of desperation. He did not like the idea. He said that we will have to live with it because it works, but it is not correct. Okay. So, he kept on thinking that it was not correct, and it was only much later in 1905 when Einstein explained the photoelectric effect, that when light falls on a metal surface, this was the experiment by Hertz in the previous century. I think it was around 1899 or something, I forget. But Hertz did this experiment, and this is the photoelectric effect experiment which some of you would have done in your undergraduate college. And the interpretation of this experiment required light to come in energy bundles, and that was some sort of a rationalization of Planck's argument. And I believe, as the history goes, Planck accepted the quantum of light only in 1908, 3 years after the explanation of the photoelectric effect. So, what he proposed in 1899 is something that he himself rejected, and it was 3 years after the photoelectric effect that he accepted that the quantum of radiation was of some significance. And as I mentioned earlier, the actual nature of the quantum of light gets established only after you understand the statistical behavior of the electromagnetic field, which was explained by S.N. Bose. And this is a copy of the letter which he wrote to Einstein. And my proposal always is to call H as the Planck-Einstein-Bose constant rather than as Planck's constant, because Planck himself rejected it. It gets established in the work of Einstein partially, but more comprehensively only in the work of S.N. Bose. And in fact, Kuhn goes on to say that it is not to Planck in 1900, but to Einstein in 1905 that we owe the origins of quantum theory. So, this is Bose, and I will draw your attention to this very nice documentary film which you can get on the YouTube, which is about the quantum Indians. It is about the contributions made to quantum mechanics by Indian scientists, specifically S.N. Bose, C.V. Raman and Meghnad Saha. So, these are very important contributions to quantum theory, and like many distinguished physicists, Bose was also a talented musician. So, he played this Esraj. Is that how it is pronounced? The Bengalis over here can correct me. Yeah. So, so I invite you to have a look at this documentary film, and you really see that quantum mechanics goes back to Einstein, relativity goes back to Einstein. The other day we talked about symmetry, and this thing that goes back to Einstein. So, this is some genius he was. So, the original beginnings, of course, were in the works of Schrödinger and Heisenberg, as I mentioned, the wave mechanics and the matrix mechanics. And basically, whenever you think about mechanics, you ask, what is the central problem in mechanics? What is the question you are asking, and how do you answer it? So, the central problem in mechanics is this: how do you describe the state of a system, and how does the system evolve with time? This is the fundamental question in mechanics. This is the fundamental question in classical mechanics, and it continues to be the same in quantum mechanics. Okay, how do you describe, how do you characterize, or how do you describe the state of a system? And in classical mechanics, from the days of Newton and Galileo and Lagrange and Hamilton, the system is described by two independent parameters. You need a minimum of 2 and no more than 2 parameters if it has 1 degree of freedom. If it has more degrees of freedom, of course, you multiply it by the degrees of freedom. But something which has got 1 degree of freedom, you need information about 2 things. One is the position and the other is the velocity. And since momentum is just velocity times the mass, you can also say that it is described by position and momentum. So, position and velocity or position and momentum are more or less equivalent ways of saying that the system requires 2 parameters. And how do they evolve with time? their time evolution is given by the rate at which they change. So, I represent position by q and momentum by p, and the rate at which position changes is given by dq by dt, which is over here q dot, and the rate at which the momentum changes is given by p dot, which is the time derivative of the momentum, and these rates are given by these equations, which we recognize as Hamilton's equations. And you can write the equivalent formulation in terms of the Lagrange's equation, which is here, which is a second order differential equation, or the Newton's equation F equal to ma if you like, and they are all completely equivalent to each other. And what these equations of motion are giving you is how is the state of the system described. It is described by q and p, and how does it evolve with time. That the rate at which q changes is given by q dot, which is equal to del h by del p, and the rate at which momentum changes is given by p dot, and that is given by minus del h by del q. So, this is the complete solution to the mechanical problem. Okay. Of course, these are differential equations to be solved. So, how do you do that? You have to integrate that equation, and when you integrate, what pops out is a constant of integration, and there are two first order equations in Hamilton or one second order differential equation in Lagrange or Newton, and you will therefore have two constants of integration, without which the solution becomes not useful. So, these two constants of integration are the initial position and the initial momentum, and you plug in those initial values of initial position and initial momentum, and you can get the complete solution by solving Newton's equations or equivalently Lagrange's equations or Hamilton's equations, which are actually based on the principle of variation. But that is another very fascinating story, but that is a different story. The solutions which come out of it tell you how an oscillator, what will be the trajectory of an oscillator in the phase space. So, the phase space is the description of the position and velocity or position and momentum. Okay. And these two being independent degrees of freedom, you plot them along orthogonal axis, and this is the phase space trajectory of the linear harmonic oscillator. And what you find over here from the conservation of energy is essentially an equation to an ellipse. So, the phase space trajectory of the oscillator is an it is an ellipse, and you can say that in the phase space the trajectory sort of settles down to what you see as an ellipse. Okay. I can say that it is an attractor in the sense that the trajectory is attracted to this particular pattern that you see in the phase space, and this attractor in classical mechanics can be a very nice geometrical pattern as we see in this, but in some other situations the attractor can be more complicated. Okay. It can be anything else, and that is when this is also an attractor because yes, you know what the limits are along the 3 dimensions. Okay. So, you can predict that okay, the system is attracted to some value inside that box, but what that value will be is very sensitive to some of the initial conditions and so on if the motion is chaotic. So, all this is in the framework of classical mechanics. Okay. And it falls in the domain of classical mechanics, and it works in a large number of areas, not because of it describes correctly the laws of nature, but because it describes the laws of nature approximately, but the approximation is pretty good in many situations, not because it is correct, but because it is approximate, and the approximation turns out to be pretty good, very good in many situations. So, there is nothing absurd about it because these are excellent approximations, and other things in classical mechanics like the Mandelbrot sets and so on. So, they all form within the domain of classical mechanics. Now, what happens is you have to get into quantum theory, which is the correct law of nature, and the beginnings are really interesting. Look at these numbers: 4101.2, 4340.1, 4860.74, 6562.10. And if the question posed to you is, do you see any pattern in these numbers? I could give you a different set of numbers 3, 6, 9, 12, 15, 18, 21 and ask a question, what is the pattern in these numbers? I can ask 5, 25, 125, you can tell me what is the pattern, right? The question is the same here, 4101.2, 4340.1, 4860.74. Now, let me give you a hint. These are the wavelengths in angstrom units of the spectrum in the hydrogen atom. So, now you would know that, okay, I have seen these numbers, but that does not help us tell what the pattern in the numbers is. Now, just think of the arithmetic genius somebody would have to discover a pattern in these numbers. There is a pattern, okay, and this pattern was discovered by Balmer. All of those wavelengths fit this formula, lambda is equal to b times n square over n square minus 4. Is it not amazing? Looking at those numbers for this man, he was a teacher in a high school and he discovered that those 4 numbers, they fit this formula. With b equal to 3645.6 and n being given by 3456. Now, this is arithmetic genius. So, he came up with this formula. This was in the year 1884, okay, and he was a school teacher in a girls' school, and that may be the reason his arithmetic was so strong. And he was able to deduce this particular formula, and he in fact went on to predict that you would have other wavelengths in the hydrogen atom spectrum corresponding to n equal to 7, 8, etc., and also that the number 4 over here could be replaced by 9, 16, 25. So, these are the square of integers as you recognize now, and this is the Balmer formula for the hydrogen atom spectrum. There is no theory for it. It is an empirical formula to explain an experiment, and the arithmetic genius of Balmer was able to explain this. Now, just 6 years after Balmer, Rydberg found a formula not for lambda, but for 1 over lambda, and he also found that this formula works. This formula is in fact the same as Balmer's formula, except that it is for the reciprocal lambda. And what is interesting about it is that Rydberg was not aware of Balmer's formula. So, he discovered it independently. So, here was another arithmetic genius who got these numbers correctly. That Balmer already knew it is a matter of, it happened, but that does not take away the credit from Rydberg. So, this is what we call as the Rydberg-Balmer formula, and this is now which requires a different theory altogether, that position and velocity or position and momentum, which we used in classical mechanics, you can write this not just in terms of position and velocity, but also in terms of a function of position and velocity, which is the Lagrangian, or a function of position and momentum, which is the Hamiltonian. And then your observables are functions of position and velocity or functions of position and momentum in the Lagrangian formulation or the Hamiltonian formulation, and you can solve problems in classical mechanics. Now, we ask this question, what happens when you begin to measure? Because we agreed that the system, the central problem in mechanics is how is the system described? It is described by position and momentum. How does the system evolve with time? It evolves according to Q dot and P dot, which are Hamilton's equations, okay? And then you must integrate the differential equations to get the 2 constants of integration, which are the position and the momentum. And if you do not know these positions and momentum, the solution is not useful. how do you get these position and momentum? Either you need a direct connection with God and he should tell you that, okay, this is the value of position and momentum, okay. And I do not really believe in the idea of God, so I do not find this alternative very attractive, okay. And then how else would you do it? You will have to measure it, right? You have to carry out a measurement, and when you carry out a measurement of one, you end up disturbing the system and you lose information about the other. Measurement of one makes it impossible to get accurate information about the other, and measurement is central to this idea. It is not because of the Heisenberg's principle of uncertainty. The Heisenberg's principle of uncertainty is because of this. It is the other way around. The Heisenberg principle of uncertainty describes this situation, that measurement of one quantity makes it impossible to measurement of position makes it impossible to measure momentum, and vice versa. And if you have to abandon this idea that, okay, now I give up, I cannot get position and momentum simultaneously, which means that I cannot solve Hamilton's equations, I cannot solve Lagrange's equations, I cannot solve Newton's equations. So, what do I do? Quit physics is one possibility, all right, or else come up with a new theory of nature, that the description of the system in terms of position and momentum did not work for me. I have to describe it differently, because if I describe it in terms of position and momentum, it runs me into a problem. Measurement of one disturbs the other and vice versa. So, I cannot use this formalism, I need a completely new theory, all right. And this means that there can be no orbits, because an orbit requires position and momentum, which also means that there are no Bohr orbits. The quantization which was described in 1913 by Niels Bohr in terms of stationary orbits, so that model cannot work, okay. There can be no orbits because an orbit requires position and momentum. It worked, it explained the hydrogen atom spectrum just the way the Balmer-Rydberg formula also did. So, it works, but not because it is fully correct. It is only half correct, which is why this is called as old quantum theory, and you have to replace the atom of Niels Bohr, because it is the atom of Niels Bohr which Niels, this is a title which was used by Banish Hoffman in her book, okay. It is a very nice book, I strongly recommend it. It is Strange Story of the Quantum. So, the old quantum theory does not work, there are no orbits, okay. And all of these cartoons in which you show these Bohr-Sommerfeld orbits and so on must be abandoned. Do not forget the three ghosts, okay. They will come after you if you use this classical picture, okay. They are not tangible, orbits do not exist. So, we have to abandon the classical description of the state of a system by position and momentum, and you need a completely new formalism. So, what is this new formalism? You represent the state of the system by a state vector, and what the heck it is, we will find out. If you reconcile with the fact that position and momentum did not work for us, you need a new representation of the state of the system. Then here you are told by those who developed quantum theory that you represent the state of a system by a state vector, okay. How do you represent dynamical variables? You represent them by operators, and these operators operate on the operands, and there is an operator algebra. And okay, are you talking about physics or are you talking about mathematics? Yes, I am talking about physics, and this is what physics is about, okay. But no, what I understand of physics is things like energy, spectroscopy, spectrum and so on. Yes, all of that will come out of this. How will it come? When will it come? And Dirac answers this very nicely in his book. Dirac says that you begin with this algebra of vectors and operators, and as you develop the algebra further, survive 1 course in quantum mechanics, 2 courses in quantum mechanics, 3 courses in quantum mechanics, all right. As you develop the algebra further, you get results which you can connect to the observables. That is physics, and this is the language of physics. This is also physics. Okay. So, the separation between physics and mathematics is very artificial. It is only in your imagination, and we have to learn about how these vectors are denoted. So, here is a notation, they are denoted by this this drawing okay, and then you have to insert some labels in it. We have to learn how these labels, how to label the state of a system. Okay. So, we will introduce ourselves to what is quantization, what are the operators which represent various dynamical variables, what happens when an operator operates on an operand. You get a new vector, what are the labels for it? Okay. How do you find these labels? Is the new vector proportional to the old vector? If it is, then you say that you have got an eigenvalue equation, all right. And if you have an eigenvalue equation, you use the eigenvalue to label the vector. Got it? The vectors are denoted by the eigenvalues of those operators of which they are eigenvectors. So, if you have an eigenvalue equation, then that is how you designate them. But what are these operators? They represent certain measurements, and some measurements are compatible with each other, some are not. And when you develop this algebra further, okay, you have to introduce statistics at some point, and this is introduced by defining what are called as expectation values, root mean square deviations, and so on. I will define these quantities as we go along in this course, and that is what leads you to the uncertainty principle, which has to be interpreted essentially in terms of the statistical properties, essentially in terms of this vector algebra which we are about to introduce now. Okay. So, statistics has to be introduced no matter what the number of particles is. In classical mechanics, you introduce statistics only because you cannot deal with a lot of information. Okay. You want to know what is the average height of a student in a class, you are not bothered about the details, and then you say that okay, it is 1.7 meters or whatever, or 1.72 meters. Okay. Because you do not want to deal with a lot of information, or like you do it in the kinetic theory, in Maxwell's kinetic theory of Boltzmann distribution and so on, right, because there is just too many particles, not because you cannot follow the dynamics. You cannot write the equation of motion for each individually, you can, but then it is too much information to work with. In quantum mechanics, you have to use statistics even if the number of particles that you are dealing with is just 1 or even none. Even for vacuum, you have to use statistics. Okay, that is quantum mechanics, because entanglement and probability is intrinsic to quantum laws, and this was the outcome of the Solway debates, as I mentioned. This is also a nice photograph which I think all of you should have with you. It is available on the internet, or I can mail you a copy. Look at the people who are in this picture. If you just read the names, almost everybody who was anybody is here. Okay? This is a classic picture of the 1927 Solway meeting. So, Dirac, Compton, de Broglie, Max Born, Heisenberg, Brillouin, Niels Bohr, Ehrenfest, Bragg, Picard, Planck, Madame Curie, Lorentz, everybody is there. So, amazing picture, all right. So, what you are finding here is the unreasonable effectiveness of mathematics in the natural sciences, and this is the title of a paper by Wigner. You are not talking about position and momentum as measurables in classical mechanics. You are not talking about state vectors, and then you are talking about operator algebra, and you are finding yourself in the realm of linear algebra. And what you will find, as Dirac tells us, as you develop the algebra further, it will connect very nicely to observables in the laboratory. The spectral intensities, the spectral frequencies, you look at the mercury vapor lamp and take a spectrum and you will see certain lines, some colors, some more intense than the other. Now, these are the observables, and all of these connections will come as you develop the algebra further. And if you trust mathematics, it will lead you to the result. So, this is the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics, which Wigner says is a wonderful gift which we neither understand nor deserve. And I do not care if we do not deserve it, we will make some attempt to understand it and use it so that we understand the laws of nature. So, this is an amazing thing that you must follow, and we have to learn what these labels are. So, the labels will give you information about the system from a measurement to which operators will correspond. You will want more information about the system, so you want to carry out one more measurement. Okay? So, you will ask what else can be measured, you will carry out that measurement, and you will carry out as many measurements as are compatible with each other, till you get what Dirac calls as the complete set of compatible observables, which will be in quantum mechanics represented by complete set of commuting operators. And then you get additional information. You have already got information about the measurement A, you get information about measurement B, and this is what quantum mechanics is about, which is to get as much information as you can about a system by carrying out the complete set of compatible observables, and this you will get from the eigenvalues of the complete set of commuting operators, and this is how you try to get as much information about the system as possible. So, this is what we will discuss in this course, and I conclude this introduction at this point. So, what instead of studying the fall of the apple, we are going to discuss the fall of classical mechanics and replace it by a theory which will involve the superposition of a cat being dead and alive, and all of this we will understand the way it has been nicely explained by Bohr, von Neumann, Dirac, and so on. Okay? Thank you very much. Questions? What we know is that there is not a single experiment done anywhere which is in contradiction with quantum mechanics. What will happen in the future is difficult to be predicted, but a lot of learned people believe that we are getting pretty close to discovering all the laws of nature which are there to be known. We are getting close to that. Whether we already are there or not, I do not think anybody has a final word on it. I do not, but I do not think anybody has. But a lot of people believe that we are getting very close to that, and perhaps maybe your generation will see 20 years from now or maybe 50 years from now that all that is there to be known is known, and if we hit that point, that is what will stay forever. I strongly suspect that quantum theory probably will stay, or it may get marginally modified at some point, if at all it has to be, but not much. In its main framework is very likely to survive, but that is only a conjecture. Time will tell. But I do not think anybody can claim this, at least at this point, that it is a final word. Likely to be, but who knows? Any other question? Okay, this is something which can be understood very easily, because the role of the equation of motion is to understand the evolution of the state of the system, which means that you should be able to predict where the system will be after delta t, after a certain time interval. So, you want to be able to predict where the object will be tomorrow or day after tomorrow, and from the equation of motion you should also be able to guess where it was yesterday and day before yesterday. Okay? So, temporal evolution, time evolution of a system is understood if you give yourself the ability to do it. Now, you cannot get this ability from position alone, because you think that velocity is nothing but the time derivative of the position. Okay? You cannot give yourself this ability, because if I give you the position of an object and say that it is moving toward east at a certain velocity, it is undergoing some forces, it is accelerated and so on, and ask where will it be tomorrow at this time, exactly after 24 hours. You will not be able to tell me unless I tell you what is its initial velocity when you start. Okay? If it already has some velocity, it may already have a velocity of 10 meters per second, it may have 22 meters per second, it could be 22 kilometers per second. The answer would be completely different. So, you have to have information about both position and velocity independently. These are independent degrees of freedom, and then you can solve the equation of motion and predict where the object will be in classical mechanics, after a given time. You do not need anything more than that. You need just these two. So, these are the 2 degrees of freedom which are required. They are independent of each other, which is why you can plot them on orthogonal axis in the phase space. You need these 2, no more than these 2, and nothing less than that. Okay? Yeah. Any other question? In principle, yes. It is not impossible. In practice, it is unlikely to happen, because what happens is that at every interaction, the result of every interaction is not unique, and you have certain probability in which the system will evolve along different pathways. So, when you reverse the process, you are not guaranteed that you will go by exactly the same path, because the pathways are not unique. Different pathways have different probabilities, which is why the entropy of the whole system keeps increasing. But each interaction intrinsically, individually is reversible. But the macroscopic expression of the integration of this process will not be reversible. It is not impossible. That probability might be extremely small, but not 0.
Sir, I have one question.
Yes. Well, this is the third derivative of the position vector. The first derivative is the velocity, the second derivative is the acceleration, and the third derivative, in fact, people have experimented with it, they have introduced it, they have done some, it is called as jerk. Okay. It is called as a jerk. But it is not useful, it does not give you any new information which the second order equation does not give. So, no new information comes out of it, so it is a useless thing. If you introduced a third derivative, you would have 3 constants of integration, and you would then argue that okay, there is a third property which characterizes the state of the system. That idea did not turn out to be useful. So, it is abandoned, it has been tried and abandoned. So, you need 2 degrees of freedom, the position and the velocity, or equivalently position and momentum, although of course one defines momentum much more accurately in terms of in the Lagrangian formulation. So, not just as mass times velocity. Yeah.
Actually, displacement can be defined as S naught plus ut plus half ut square. It has a displacement term and velocity term as well as acceleration term.
Yeah.
Acceleration term, if you see, of at square.
Yeah.
T power square is there, and we like T power cube terms are there for few examples. For example, Coriolis deflection, deflection due to Coriolis force.
Okay, you have to remember that the Coriolis is a pseudo force.
Okay, yeah.
So, in the actual interaction that we talk about, what we talk about when we refer to the physical interactions, you are not talking about pseudo forces. If you carry out analysis in an accelerated frames of references, you may end up with all kinds of terms. If you describe the motion on Earth in a frame of reference which is on some other planet which is accelerated around some other star in another galaxy, then all of these accelerations of that galaxy with respect to our galaxy, the acceleration our solar system has, our planet has, they will end up adding all kinds of terms, t cube, t to the n, what not. They do not correspond to real forces. So, if you do your analysis in an inertial frame of reference and you deal with the fundamental interactions that we know, which is gravity, electromagnetic and nuclear strong and weak or some unification thereof, then you do not need anything more than 2 parameters, position and momentum, and a second order differential equation, that is it. You do not need anything else. Yeah.
Although it is pseudo force, but it is affecting on the real situations.
Yes, it is effective, means it is not affecting, it has an effect which you think is real, not because it has done anything to you, but because you are in an accelerated frame of reference. Okay? So, you will have to invent that because you want to describe your acceleration as proportional to some force, because you are very much inspired by Newton's law. So, you rewrite Newton's law in the same terms, but now you write it not as F equal to ma, but as F prime equal to ma, where F prime is different from F. So, it is because of the pseudo forces. So, it is not because there are real interactions, there are no real interactions. Real interactions are only these, the fundamental interactions. Okay, so thank you all very much. Any other question or?